All right. Well, good morning, everyone. First of all, thank you, Dr. Gupta, for inviting me to give this presentation in the inaugural spotlight session of JSI's. Pleasure to be here today. So today I'm going to present our work on an image-based approach to variational path synthesis of linkage mechanisms. And this is the work that was done with my PhD student, my former PhD student, Srinath Deshpande, who graduated last year. So this is based on the paper that was published in JSI's as well. So in this presentation, actually, I am not going to focus a lot on how we do certain things, but give you a little bit of an overview of what we are doing here, what is the problem we are solving, and why we are doing this. Okay, because a lot of technical details are already available in the paper, so I will spare the details in this presentation today. Okay. So this is quite a mouthful. The title, the image-based approach to variational path synthesis of linkages. From that title, probably you can tell that we are concerned with the problem of path synthesis of linkage-based mechanisms, which is basically the problem where you are given a path by somebody and you are trying to create a mechanism that can follow that path, right? A particular point of the coupler. And again, this is not a new problem, but I'll have more to say about that. So what is this deal with the image-based approach? Well, this is where we are bringing together three separate disciplines, right? We're talking about pattern recognition, we're talking machine learning, we're talking about mechanism synthesis, all these three things together to basically solve this age-old problem, but perhaps we have a new outlook. Let's see. So this is the big question. How do we synthesize mechanisms that trace a path, right? And more precisely, how do we synthesize mechanisms where a particular link, one of the coupler links or the floating links, traces a certain path, right? And what you're seeing here on the left in the cartoon is a sit-to-stand mechanism for helping somebody get up from a seated position. And you can see two traces here, two paths over here. One that looks like kind of, which is imprecise, and another one that looks like a perfect S-shaped path. And these are the trajectories of the hip joint when you get up from a seated position and come down. So the objective over here from a designer point of view might be to design the mechanism that can trace this path, right? But even before we get to that problem, well, we have to ask ourselves, what is it that we are really trying to do here? Okay, what is the big problem? The big problem probably starts with having some sort of product design specifications in terms of what you're trying to design, right? Having functional specification, having a specification on the size, right? And most of the time, those specifications are to be satisfied simultaneously, right? And there sometimes they might be in conflict with each other. So it's no longer just a problem of designing a mechanism that traces a certain path, right? You might have constraints on where the fixed pivot should be located. You might have constraints on where the mechanism is allowed to go, right? It shouldn't be hitting the chair. It shouldn't be obstructing the motion of the human body itself. So generally, you have a lot more constraints than just the path problem, okay? The other thing is that when you want to solve a problem like this, if you look at the existing kinematic literature, it talks about what is known as precision point approach. So what it does is it takes that path that the user provides and it converts them into a set of points along that path. And now you set up some sort of equations, you create an optimization formula where you try to minimize the path traced by a coupler of a mechanism versus the path that is given to you. And in the process, you find the dimensional parameters of the mechanism, right? Now, that's really a computational convenience for you, okay? And what results from that is maybe a few solutions, okay? But now if let's say the designer is not happy with any of those solutions, then where do you go from there? Well, you can say, all right, I'm going to, change something about my input and see if I can get a different result, right? Now, most of the time, designers want some agency in the process. It's no longer just about giving an input and getting an output, right? If an input is not good enough to produce a solution that is acceptable to the designer, then there should be some guidance, there should be some feedback to the user that these are the possible things that you can change, right? So the name of the game is interactivity, right? How do we make sure that the designer has agency in the process? So there are problems on how we formulate the problem, there are problems on how we solve the problem, And then there are, of course, problem with what comes out at the end of the solution, right? And on the right-hand side, you can see a few different mechanisms that can be potentially created if you are willing to sacrifice the precision of the input itself. So you can see that the perfect shape stays the way it is, but you have different kinds of mechanisms. Some of them are 4 bars, some of them are 6 bar, and so on. All right. So that's the big problem we are talking about over here. Now, the question is the approach that we are taking, an image-based approach, how could that potentially help us, right? This is where we think machine learning can help, because mechanism designers in the kinematic literature have done a lot of research in this area, okay? But they have been rather limited in terms of how they solve the problem and what kind of solutions they generate. So when we take an image-based approach, basically what we are saying is that we can take that input provided by the user and we will turn that into a spatial signal. Now, the current approaches have been mostly based on treating the input as a temporal signal, right? Time parameterized signal, which works. But then the problem is that you have to create a methodology to solve these problems, which is specific to the type of mechanism that you have picked. But by making that signal, that input into a spatial signal, the hope is that you don't have to worry about the algebraic complexity of these input curves, right? So, we know 4-bar mechanisms, coupler curves are degree 6 algebraic curve. 6-bar have even more complexity and so on. But if you treat them as an image, then they just become a bunch of pixels. And pixels, they don't really care which mechanism they come from, whether it's a 4-bar or 6-bar or 8-bar, right? So that's the basic idea. And now the hope is that we can employ some sort of deep generative model to understand the probabilistic distribution of those curves and hopefully be able to synthesize a large number of conceptual design solutions, which is what the mechanism designers are generally looking for. They're not looking for 1 or 2 solutions. They're looking for a large number of solutions from which they should be able to pick. Okay, so that's the overarching goal of this work. Be able to provide the designer flexibility in terms of how the input is specified, in terms of what kind of solutions are generated. And if a solution is not satisfactory, then what kind of feedback you can provide to the user so that he or she can make the changes to the input and get better solutions. Okay. All right. So, we all know that kinematic synthesis in the machine design pipeline is the most critical stage, right? Because we know that no amount of sophisticated programming and electronics will solve the problem if your design of the robot or the mechanism is not a good one, right? And as I mentioned before, typically this starts by having a list of criteria and specifications for the robot or the machine. Then the designer's job is to take some part of that specification and convert it into what is known as a kinematic task, right? And this is an important step because if you don't formulate a good kinematic task from the specification, then you end up actually creating solutions which may be completely undesirable, right? So this X task over here is important how you specify that. And one of the ways, as I mentioned before, is you take a continuous curve, if that's your input, and you convert it into a bunch of discrete points along that curve, and that becomes your synthesis task. Now you can employ your solvers, which might be based on some sort of algebraic formulation and do the optimization to reduce the distance between the given input and the coupler curve. And hopefully you can get some solutions which might be useful. But we know that most of the time the solutions that you get are defective solutions. So the space of the useful solution is kind of narrow that comes out from the traditional solvers. And once you have some solution, hopefully you can do the detailed design, right? So we understand this very well. And you can see there are 2 boxes over here. So I'm going to focus on the left side, which is more like the kinematic task formulation. And I'm going to focus on the synthesis side and reiterate basically what I just said before, okay? So here is our sit to stand problem. And I'm just going to use that as an example for this over here. And then the designer has to create the kinematic task. And you can see the precision points, right? This is the traditional approach. And this is largely a computational convenience because we know how to solve problems like these, right? Once we convert a curve into discrete points, then we can write a set of equations and we can minimize the error between the two and we get our answers. But this is not the problem. Remember, this is just a translation of the original problem that was presented to the designer, okay? Synthesis methods are too specific, so they generally work for one type of mechanism, but then you want to create it for another type, let's say 6-bar, 8-bar, then you have to come up with a difference of solution methodology, and then each of them will always give you narrow outcomes, right? Limited number of solutions, and some of which may not even be useful because they're defective in some sense. So as I mentioned before, the question is, can generative models help over here, right? So the idea of the generative models is that you have different types of mechanisms, right? Let's say, a Stephenson 6-bar, 4-bar, and a slider crank. And each of these types of mechanisms, they have their associated parameters, right? Dimensional parameters of what their length are, where the fixed pivots are, where the moving pivots are. And they all can create different kinds of cuts, right? This is something that we know. So in the domain of all possible two-dimensional curves, you get only certain kinds of coupler curves, right? I mean, this domain is much larger, and then you can see that slider crank is within the domain of 6-bar and 4-bar, and then you get curves which are completely outside the domain, right? So these three that you see over here basically cannot be traced by 4-bar and 6-bar mechanisms. Maybe 8-bar, 10-bar, I don't know, right? So these are the sort of the space of the curve. Now, in a deep generative model, our hope is that we can learn the process by which these curves are actually generated. Okay, that's what we want. So what is the natural process that generates these curves? Can we understand the relationship between the coupler curves created by these mechanisms and the dimensional parameters themselves, right? So in general, most of the deep generative models like, GANs and VAE is what we will be using in our work. They have two parts. They have what is known as an inference or recognition model, and then they have a generative model, right? So the inference model's job is to basically learn this probabilistic distribution of the coupler curve. So you can see that, these different regions, the purple, green, and the pink, they map to different parts in a much smaller dimension, much smaller dimensional space called latent space, okay? And then these become basically singular vectors in there. Now, if you use a variational autoencoder kind of architecture, then these are no longer singular vectors, but they're more like probability distributions, okay? And once you have understood that, then you can generate new coupler curves, new mechanisms by going in the reverse direction. So you have an inference model that infers the properties of the coupler curve, understands the probability distribution, and then you have a generative model which can go in the reverse direction. You can sample in this latent space, and you can create new coupler curves which correspond to new kind of mechanisms. So that becomes sort of the basis for generating a large number of solutions, defect-free solutions, and also in the process understand how the input, how well the input is presented by the user, and if you can provide some sort of conditioning on the input if it is not conducive to design, okay? So as I mentioned before, we are using image-based representation of the coupler curves. So what we want to do is we want to take a bunch of coupler curves generated by different mechanisms, and we want to first normalize them. So they fit it within a standard size, and then we discretize them. And here we are using a 64 by 64 image because that seems to work very well. Convert into a grayscale image. So every coupler curve is basically discretized into a bunch of pixels. So now what we want to do is we want to learn the spatial correlation among the pixels so that we can figure out whether they're coming from a 4-bar or a 6-bar and so on, okay? So the architecture we are using is a CNN VAE architecture. It's a, CNN variational autoencoder architecture. So a variational autoencoder architecture is basically a spin on a traditional or a standard or a vanilla autoencoder architecture. In an autoencoder architecture, you have a recognition part, you have a generative part, and essentially its job is to compress it into some latent space. So this layer over here you're seeing is generally the latent space, and it's a much smaller dimensional space. So the idea is that this whole system, this whole network learns the essential properties of the input and compresses it into the latent space, and then you can sample from that space and regenerate your input, okay? But in a variational autoencoder, you basically make this latent space to be a probabilistic distribution instead of being singular vectors, and that helps us generate new solutions. So this is how this pipeline works. You have an input which has been discretized into a 64 by 64 image. It goes through the recognition network, and you have, CNN, you have a convolution layer, you have ReLU layer, you have a max pool layer, and you might have more than, one layer over here. And then it compresses the essential properties of this is compressed into the latent space. And then you can sample, and this is forced to be a Gaussian distribution. it is forced to be Gaussian, and then you can sample from this Gaussian and go to the generated network and recreate your input. And you can see that it's similar to this one, but it's not exactly identical, right? And the whole idea is that you want to basically maximize your evidence lower bound, okay? So this left part over here is the reconstruction error, how well you're going to reconstruct your input, and the right-hand side is about what is known as the KL divergence. So essentially what you want to make sure is that your latent space is well behaved. Okay, so you have clusters, but you don't have too many of those, and all these clusters are close to each other so that there is some there's some continuity across the latent space, and you can do things like interpolation between the subspaces and so on. Okay. So that's our architecture. Now, what can we do with that? So here is our way to do the feasibility conditioning, right? And this is, so when we say that we have an input task and we call it a feasible task, it can go through our CNN VAE architecture and it can give you reconstructed input, right? Now, when you look at the reconstructed input, you know that it's not going to be identical to this unless it came from a known 4-bar mechanism, which can be exactly generated. So the difference between these two will tell you basically how well this can be actually generated by the 4-bar mechanism. And we call this probability of generating a task given an input task. So X hat task is on the output side, that's a reconstructed input, and X task is your input, which is what we call the raw input, right? And that is approximated by our CNN VAE architecture over here. So for this particular example, you can see that there's a high probability of pretty much all the pixels being recreated by a 4-bar mechanism, right? How do we know this? You can see that 70% of the pixels have probability 1.0. So 1.0 means that you're able to generate that pixel exactly. And if you have low probability, that means it's not possible. Now look at one of these tasks, which is what we call an infeasible task, because the 4-bar will have difficulty creating this kind of spiral curves. So it tells you, the regenerated curve tells you basically what would be possible for you. And you can see over here, the probability is all over the place. 1.0 probability is done by only by 17.5% pixels. So here is another image that shows you basically it gives you some feedback on the input, right? That's your input image over here. And it tells you that these are the parts which would be hard to do for a 4-bar mechanism. This one even harder, so you can see it becomes even more pixelated, and this is the one that I presented before. And the green one basically shows you the probability shift or the difference between these two. So the dark regions are harder to capture, and the lighter ones are easier to do. Okay. So now what can we do with all this stuff, right? So we can do the input conditioning, we can give the feedback to the user, and now if you want to create a large number of defect-free solutions, what do? Well, we use the same architecture, right? So you have the raw input, you normalize it, you discretize it, you throw it into the variational autoencoder architecture, and now you have a point in the latent space. But we know this is a probabilistic distribution and a Gaussian, so we can sample from the space, right? So what we do is we do a k-distributed neural network queries, and within the vicinity of the point for this, we can actually generate a large number of coupler curves. Some of them may not even have been seen by the network before, okay? And we can get the probable inputs, but by doing these queries, you can create a large number of 4-bar and 6-bar solutions. So far, we have trained our network with this 4-bar and 6-bar, which are the most common linkage systems, and we can generate new solutions from that process. So here you can see an example of different kind of mechanisms that exhibit this spiral nature. Okay, so you can see this is what the user inputted, and again, the user doesn't care exactly about this path, but has some spiral nature. This is the conditioning on the input, the mechanism. Here is another one that has the spiral nature. Okay, all right. So let me show you a quick demo of how we do this in a homegrown software called MotionGen. So I'm going to quickly share my browser window. And this will be fast. Okay, so this is where we can actually sketch it, and this is something that we've developed ourselves. We can sketch a path. So what I'm going to do is I'm going to draw a path, and I'm doing this in my browser window. And the software basically synthesizes different mechanisms, and we can basically go through these, right? So you can see that it's not the exact same path that I drew, okay? but it is close enough to that. And we are getting all these different solutions, some of them 4 bars, some of them are, so this is a 4 bar, before we were saying 6 bar and 8 bars, I think. That's another 4 bar mechanism that, follows this. This is another one. So we have, and these are done via the KNN queries, right? And we can enlarge the space. So at any point, if the user says, you know what, I'm not happy with these 30 solutions you're giving me, I want more, and we can provide some sort of interface where the user can tweak the parameters and say, all right, I'm willing to have a few more solutions if I can, if I can change my path slightly even more than what I have drawn over here, and you can get more and more solutions out of it. All right, so that would be it. Thank you very much.